Okay, welcome back everybody. Lecture 19, Math 131. Tomorrow is the opportunity to show what you know on paper. And test 3 begins at 4.4, which is natural logarithms, the derivatives of natural logarithms, etc. But as you will recall, you can't handle natural logarithms unless you can handle natural exponential functions, because sometimes you're going to have to solve or you're going to have to know some identities. So even though the test officially begins at 4.4, be sure you're reviewing your natural exponential functions. Okay? Then it goes through the applications, 5.1 and 5.2, which is the applications of the natural exponential function. Shampoo, you've got your differential equation. The solution is P e to the RT. If your R is positive, it's growth. If it's R is negative, it's a decay. And we also looked at it in terms of money, but don't forget your little differential equation, because that was the new part. It says how something is changing with respect to time. Then we jump over to chapter 6, and that's our beginning of integration, our anti-differentiation. And 6.1 was the basics. 6.1 was the integral of x raised to the r dx. The integral of e to the x dx, and the integral of 1 over x dx. You had 3 types of basic integration problems you were going to work with. What I always do is go directly then to 9.1 for integration by substitution, where you now have a function of x, and it's u to the r. Now, what was the restriction on the r here, by the way? R is not equal to -1, because if r is -1, then you're at 1 over x. And then we had the integral of 1 over u du, where u is a function of x, and the integral of e to the u du. Okay, so we jumped and worked on 9.1. Then in 6.2, we did Riemann sums as a way to approximate a definite integral. And those are the y values times those widths, and we had left endpoint, right endpoint, midpoint for doing those. Then we moved into 6.3 and 6.4, which was getting your curves and finding the area. They called it under the curve, meant from the curve down to the x-axis. I tried to call it area between or bounded by, and we looked at finding the area using the definite integral. All right, and so 9.3, of course, was integration using substitution for the definite integral. All right, the first thing that I'm going to do is go through some specific homework questions, and then we'll turn the pages and see if it alerts us to anything that we need help with. All right, so what I want to do is kind of go in reverse order, since area bounded by curves was the last thing we covered, and you've had less opportunity to ask questions for that. And I'm just going to go directly to WebAssign. These are questions that somebody asked before class. This is in the section on integrals and areas. This is WebAssign, integrals and areas under curves. And it's, what question is that? That's problem number 3C. Okay, 3C. Somebody print it out for us. It says, find the area between the curve y equals x squared minus 4x and the x-axis. So that's really more nicely said than sometimes. It just says find area under the curve. But this is the area between the curve and the x-axis, and x is going to go between 1 and 8. All right. Anytime that you're going to find the areas, work with areas, it's very important that you sketch the graph, because you have to know which curve is on top and which is on bottom, because you're summing up areas of little rectangles. So as soon as you see y equals x squared minus 4x, you immediately know that's the graph of a parabola. So let's get a picture of what the graph looks like. All right, so it's y equals x squared minus 4x. All right, it's easy to find the x-intercepts. Easy to find the x-intercepts because it factors. So it's going to cross through the x-axis, let y be 0, where x is 0 and where x is 4. Okay, this person had already figured that out right here. Okay, those are the x-intercepts. I'm just trying to get a visual of the graph. All right, so we know the curve is going to do something like this. All right, we don't have to be perfect. We just have to know where it's above the x-axis and where it's below. All right, the instructions are to find the area between this curve, the x-axis, for x being between 1 and 8. Okay? All right, so this is telling me I want x to be between 1 and 8. So when x is 1, we are right here. So here's x at 1. I'm just going to sort of highlight here so we see it. And of course 8's way off my page here, but we'll put 8 over here. This is not exactly drawn to scale. The idea though is, can we see what kind of area we're talking about here? And here is x at 8. Okay, so it says between this curve, the x-axis, here's the x-axis, from x equal 1 to x equal 8. All right, now I'm going to show you what each person has done. I think I'm going to show you what each person has done. That's a different problem. Okay, show you what this person has done and you tell me what you think about it. All right, everybody see it? Okay, this person integrated from 1 to 4, x squared minus 4x dx. Okay. Exactly, exactly. This is bottom curve minus top. And we are looking at an area, so we have to have a positive height. So when you come in here, always put in your little element of area. And you're looking for what's on top and what's on bottom. And you've got to start at x equal 1, and we're going to move all the way over to 8. But we notice after 4, the top curve and the bottom curve change. Okay, top curve and bottom curve change. So we are only working from x equal 1 to x equal to 8 because the problem told us to do that. So how do we get this first little area? We're going to sum up from 1 to 4. And the top curve is, what's the equation of the x-axis? Y equal to 0. So 0 minus, be sure to use parentheses, x squared minus 4x. Okay, that's top minus bottom. That gives me that height right there is a positive number, dx. Okay, plus, now we're going to pick up at 4 and go to 8 because the problem told us to go to 8. And once I pass 4, the top curve now is x squared minus 4x, and the bottom curve is 0. Okay? All right, so important that you sketch the graph so you can tell top curves and bottom curves. All right? Everybody good? All right, I'm not going to finish that. Just clean it up, integrate, and go for it. All right, if you set up wrong, then you're sending yourself on a major tangent. If you don't draw your graph so that you can see tops and bottoms, then you've got it all set up anyway, incorrectly. All right? Okay, can we check that one off, everybody? Okay, so that was number 3C. 3C. All right, the next question was 3D. Okay, we had two people asking the questions about 3D. And we're in the same homework set, which is integrals and areas under curves. All right, and here's the question. And we have two, what did I do with the word? All right, here's the question. Find the area bounded by the curves y equals 8x cubed plus 3 and y equals 8x plus 3. Find the area bounded by those two curves. Alrighty, so I actually have the work of two people who got it incorrect, so let's, and did anybody show me a graph? Yep, you showed me a graph. Alright, let's look at your graph. Alright, y equals 8x cubed plus, I already found your mistake. Did you have a 3 or a 2 here?
The graph was wrong.
Excuse me?
This is not a correct graph.
That's not a correct graph. I think you might have copied that wrong. And also, if it's x cubed, it's not going to look like a parabola. All right, so we know the graph's wrong. All right, so let's sketch the graph. Y equals 8x cubed plus 3, and then we will graph y equals 8x plus 3. Okay, y equals 8x plus 3 is going to be easy. I'm just going to, so to get a little sketch here. All right, 8x plus 3, everybody knows that's the graph of a straight line, right? Y-intercept is, I wanted to do that in green. Y-intercept is 3. Slope is 8. So I'll go up 8. 1, 2, 3, 4, 5, 6, 7, 8. And over 1. Okay. Ooh. Try to draw that somewhat straight. Okay. Now, 8x cubed plus 3, we're looking at the graph of y equals x cubed. We're going to do some transformations. What does the graph of y equals x cubed look like? Yep, that's one of your basic graphs. Y equals x cubed looks like this. Goes through the point 0, 0, 1, 1, negative 1, negative 1. Okay? And what do we do to those y values of x cubed? Multiply them times 8. All right, so 0 times 8 is 0. 1 times 8 is 8. So the next transformation is that we would have 1, 8. And negative 1, negative 8. So this would be the graph of y equals 8x cubed. Okay? And the next quick transformation is, what are we going to do? We're going to shift everything up 3. Up 3. So now, let's do that in blue. So if we add 3 to the 0, we now have 0, 3. We now add 3 to the 8, and we now have 1, 11. And we add 3 to negative 8, and that would be 1, negative 1, negative 5. Okay, so it's the same graph as y equals 8x cubed, except it's been shifted up 3. Okay? All right, so that helps us know pretty quickly, just reviewing those transformations real fast, how to graph it. Now, this point right here was 1, 11 on the green, and if you notice it, it is also going to be 1, 11 on the purple, so it's going to go through right here. So now your question is, really, is it underneath here or is it on top of here? And when they look like they're on top of each other, what do you need to do? Check something in between, all right? Because we already see those intersections. I would bet that it's going to do like this. But just to be sure, let's check. x equal a half. Okay, if I put a half in for the line, I would get 4 plus 3 is 7, right? So this would, at a half, it would be 7, half 7, right here. 1/2 7. If I'm on the 8x cubed plus 3, if I put a half in there, what am I going to get? 1/2 cubed plus 3. Half cubed is 8, 1/8. 8 times an eighth is 1. 1 plus 3 is 4. So 4 is going to be, this one was at 1/2 7. This is going to be at 1/2 4. So that sort of helps you see right there. It's going to come like this. Okay. And let's see what's going to happen on this side. I have a feeling, and we'll know that for sure once we set up our points of intersection. But when x is equal to 0, let's see. Excuse me, when y is, that one's hard to tell what that is. Let's pick a value and go for it. All right, so I think that's what's going to happen, but let's just double check. All right, this is going to cross through when y is equal to 0. That's going to be a negative 3/8 for the green. This is a negative 3/8. Negative 3/8. If I let y be 0, x is negative 3/8. Okay, over here, if I let y be 0, we have negative 3 equals 8x cubed. X cubed is negative 3/8. And then I'll take the cube root of negative 3/8. Let's just see what that is. So we got minus 3 divided by 8. And we're going to take that and raise it to the, that's negative, it's cube root. Raise it to the 0.33333. That'll give us a pretty good idea. Not quite sure what this did for me. All right, so we'll go negative 3 divided by 8, enter, and I'm going to raise it to the parentheses 1 divided by 3. That's better. Negative 0.7, it's about negative 0.72. And what's 3 divided by 8 to begin with? 0.37. So this is about negative 0.37. This is coming in at about a negative 0.72. So that sort of told you where it was with respect to the green line. All right? So I think I have that drawn pretty correctly. Now, did you find your points of intersection? Not sure if you did or not. All right. How do we find these points of intersection, the x coordinates? Set them equal to each other. So we got 8x cubed plus 3 equals 8x plus 3. All right. The first thing we notice is that the 3's subtract out. So we have 8x cubed equals 8x. So let's get everything on one side and set it equal to 0. 8x is a common factor in both terms, and we have x squared minus 1. So our values for x that make this equation equal to 0 is x equal to 0, x equal to negative 1, and x equal to positive 1. So they're intersecting right there at negative 1 and positive 1. All right? So we're ready to go now. This is negative 1, and we already knew that was positive 1 because we saw it. All right, half the battle is getting the picture drawn so you can see top curves and bottom curves. Are we ready to go? All right. Let's start. We're going to integrate, and let's start over here. And remember, you want to put in a little element of area so you can see which curve is on top and which is on bottom. And over here, do you see the top and bottom curve changed? All right, so we're going to sum up from where to where? To start with. Negative 1 to 0. And my top curve is the purple. 8x cubed plus 3. Minus. The bottom curve is the green. dx. Please, please be very careful to use your parentheses because it's top minus the entire bottom. Okay? And then we will pick up at 0 and we'll go to 1. And the top curve now is the straight line. And the bottom curve is the third degree polynomial function, which is 8x cubed plus 3 dx. And be sure before you try to integrate, you always simplify in your integral, and it will just make your calculations easier. You can already see the 3 and the minus 3 are going to cancel out. All right, is that good? Those who ask? Okay, I think just making the observation is the problem was the curves were not sketched or sketched accurately. And you want to be sure that you can sketch lines, that you can sketch quadratics. These are fundamental. That you can sketch a square root. That you can sketch basically a 1 over x kind of deal. And that you can sketch a x cubed and an absolute value of x kind of problem. Okay, those are kind of fundamental. I think those are the 6 basic graphs that you learn to do transformations with to get the sketch. All right, everybody good? Okay, the next question that I got, let's see, was all right. This is from homework 12. And this is problem letter D. Letter D. All right, and it is the integral from 0 to 2 e to the 7x dx. All right, homework number 12, letter D. All right, I want you to look at the work. And I want you to tell me what's wrong with this. All right, what basic form is this fitting? All right, this it looks like it needs to be e to the u du problem. Now, you want to always show all your work. It's got to fit right back in. All right, and this is all we see for this work, and so that would be minus full credit on this problem because I have no clue what you're doing. I can't follow your thinking process. So let's work this one together. What is your u, everybody? 7x. So here's your e to the u. I should come right underneath it and do it. See if I can. E to the u. All right, then what's the next step, everyone? You got to find the du part. So du is 7 dx. Once you find your derivative, what do you need to be careful to do? Look, I've got a dx. I need to solve this for dx. So 1/7 du is dx. So in the place of dx, I'm going to put in 1/7 du. All right. Now yesterday we looked at changing the limits on the integral so we never have to go back to the x's. And I personally like doing that, so that's what we're going to do. When x is equal to 2, what is u equal to? U is 14. So we can put a 14 up here. When x is equal to 0, u is equal to 0. All right, so now we're integrating from 0 to 14, e to the u, 1/7 du. What's the formula if you integrate e to the u du? It's just e to the u, whoops, plus c. There you go. E to the u plus c. All right, so we have a e to the u, and 1/7 is just a constant, so we'll have 1/7 e to the u. And since we are evaluating the definite integral, we can leave the plus c off. And u is ranging from 0 to 14. All right, I'm not sure what you were trying to do here. It's a straightforward e to the u du problem. That just answered your question? A lot. Okay. All right, I'm going to slide right into your question, if that's okay. Questions here? All right, I had another question, and this came from a homework. Was that a homework webassign or out of the textbook? A webassign question? Okay, homework 14, question F. It was x e to the 2x squared dx, and you were thinking it was going to be a e to the u du problem. So you called your u 2x squared. And so you came under and you went e to the u. Okay, then you took the derivative. And you did everything just right. You just lost your confidence in there. You noticed up here was a x dx. And x dx is 1/4 du. So right here, this is not a good statement. You have already done your e to the u. Now the x dx is exactly what you said it is, 1/4 du. All right, and so once you know how to, you've got e to the u du, it's just e to the u plus c. And this is an indefinite integral, so we don't need to worry about converting any limits on the integral because it's not there. So it's going to be 1/4 e to the u, which is 2x squared plus c. How do you check this? Just remind me, how do you check this, everybody? Take the derivative. So let's do a check. You don't care if I write all over your paper, do you? All right, let's take a check. And remember I said you got to know all about natural exponential functions on this test because to check a log, you got to be able to go both directions, and you've got e's on your integrand, so be sure you review that first part of chapter 4. All right, if you take the derivative, okay, it's going to be 1/4 times. Now, what's the derivative? This is chain rule. What's the derivative of e raised to a function? E raised to that function times the derivative of that function. Okay, and then, of course, the derivative of a constant is 0. So when we clean this up, the 1/4 times the 4 cancels out, and you're left with x e to the 2x squared. Check. Okay? Everybody got it? All right. Another question that was asked. This is a homework question, I think. I mean, a textbook question from 9-1, page 455. Number 8. Okay. So it is 1 plus the natural log of x, quantity raised to the third, over x dx. And right here, the person likes to do it like me. I like to write it as a product so I can see everything. Now, as soon as you see this, you have some function raised to a third power. So it's making you think, which form do I want to try? What is it making you want to think? Looks like it might be a u to the r du. Now, if you guess wrong, you're going to know it because things are not going to fit. And you don't get upset. You just go, this is a game. Now I'm going to try another route. All right? You have to decide what form you think. All right. So this raising this x to the -1 probably didn't need to go there yet. So you said, all right, let me rewrite this so I can go right underneath it. So I'm copying what you did. 1 plus natural log x cubed times 1 over x dx. So you said, I think I'm going to let u be 1 plus natural log of x. So you call that u to the third. Perfect. Then you took the derivative. When you look both ways, that's a perfect du. Perfect du. Okay? And so when you integrate a u to the r du, when r is not -1, it's just u to the 4th over 4 plus c. And so putting back in what your u is, you have 1 plus natural log of x now raised to the 4th over 4 plus c. And you had it correct except for the plus c, but you just weren't confident. Okay? If it fits like a puzzle, you're on the right track. If it's not going to fit, then you may have your wrong thing. Is it u to the r, e to the u, or du over u? Okay? Is that good? All right, let's see. Did that take care of all the questions you guys gave me? Think so. All right. So let's talk through the chapters and make sure we have everything ready for the test tomorrow. All right, and let's begin back at section 4.4. By the way, you remember how I told you this book is trying to tell you a few things before you ever need it? Back in section 4.3, they actually introduced to you a differential equation, which we used in chapter 5.1. It said, determine all solutions to the differential equation y prime equals minus 4y. Why is that called a differential equation? It's got a derivative in it, it's got an equal sign, and our derivative is redefined in terms of that function y, which we don't know what that is. All right, but what would be the solution to this? Tell me what the solution is.
It's decay.
It's going to be what? We don't know what formula you're going to head to for a solution to the differential equation.
Exponential decay.
P sub 0 e to the RT. All right, what's the solution for this going to be? We don't know what P sub 0 is. So P sub 0
e to the negative 4
e to the negative 4 t. All right. Okay, this is in section 4.3, even though, this is really just kind of reviewing you for section 5.1. Y prime equals minus 4y. All right, we looked at P prime of t equals R P of t. I was trying to get my right letters in there. All right, here these are just different letters. If y is a function of x, if y happened to be a function of x, then the solution here would be y equals y sub 0 e to the minus 4x, if our y is in terms of x. What we had before in chapter 5 was where we were applying it, and we said P of t equals P sub 0 e to the RT. Our function was in terms of time. So here it's just using different letters. Do you see? It's still like P sub 0 e to the RT, except you're using x's and y's. All right, I just saw that right here in section 4.3 where they were trying to get you there.
In the beginning of the class when we learned that big long equation for the solution of the difference equation.
Difference equation.
Difference equation, that's right.
Okay, this is differential equation. Okay. Two big differences. Okay. All right. Let's go through the chapters. I'm on page 261. Just reminding you of some of the identities for natural log. Natural log of 1 is 0. You'll remember the graph of the natural log function is the inverse of the natural exponential function. Just a reflection there. You have an asymptote on the y-axis. Couple identities that often come into play, and you'll remember when we did log differentiation, this came into play. E to the natural log, and it really doesn't have to be x, it could be a. E to the natural log of a is equal to a, or e to the natural log of x, whatever x is representing, is equal to x. Of course, x has to be greater than 0 because the natural log of x is defined for all values of x bigger than 0. That's why you have that vertical asymptote there. All right, and the other identity, is that the natural log, which is log to the base e of e to the x is x, or natural log of e to the a is equal to a. Okay? Just flipping through some pages. I'm on page 264, exercises 4.4. This was really your algebra review, learning to simplify expressions so that once you started working with the derivatives or integrating, it was going to be easy for you. Solving log equations and exponential equations. When you have an exponential equation and the variable's up in the exponent, what are you going to do to both sides? Take the natural log. When you have a natural log equation and the variable is part of the argument, what are you going to do? Let both sides be the exponent for e so that you can use those properties there. Okay? And like in number 33, before you could let both sides be the exponent for e, what do you need to do? Divide by 5, because it's got to be the natural log on a side by itself before you raise it to the e power. Okay, so you would divide by 5, and then you'd say e to the natural log of 2x equals e to the 8/5, because the identity back here is the 1 natural log of e to the power, or 1 e raised to the natural log, not some number in front of that. Okay? Everybody remember that? We're on page 262, and this was page 264. All right? Okay, so section 4.4 was just a review of your natural log function. All right, looking back at 266, this was really hard. The derivative of natural log x is 1 over x, just 1 over x. When you read a problem like this is in the example 1, y equals, read this problem to me. X what? Times natural log x. When you get ready to take the derivative, what rule? Product rule. Read problem A. Natural log of x. The whole thing is raised to the 5th. What rule are you going to start with? General power rule. Is this the same thing as? No. This is not equal to natural log x raised to the 5th. Okay, this is only the x that's raised to the 5th. Only the x. Okay. When you see, let's see, where's another problem? Don't see one. Okay, this is telling you the derivative of natural log absolute value of x is equal 1 over x. I think we derived that in class. I'm pretty sure we did. Tell me how are you going to deal with number 7 for finding the derivative?
What is raised to?
Okay, suppose I told you simplify first and then take the derivative. How would you simplify number 7? All right, what property are you using? Okay, but there's then another plus x. This is not equal to e to the natural log of x plus x. It's not that deal. It's e raised to the natural log of x and then a plus x. How can I simplify that before I take a derivative? Yes, properties of exponents. A to the m times a to the n equals a to the m plus n. So this is equal to e to the natural log x times e to the x. And then what do you know about e raised to the natural log of x? X. So I have x e to the x. All right. Now, if I'm going to take the derivative, what rule am I using? Product, because it's x times e to the x. X times e to the x. That's only if I told you you had to simplify first. I just wanted to remind you of some of these properties. You don't have, the book didn't say you must simplify first. If you didn't simplify, the derivative of e raised to the u is e to the u times the derivative of the u part. Yes, very good. Okay? All right, let's see if we see another one on here. How are you going to deal with number 16? How would you do number 16? You could do a quotient rule. Okay, or you could, yes, or you could write natural log of x raised to the -1 and then do your general power rule. Okay, I was looking for a quotient. I don't see one. Okay, I don't see anything there. All right, what about number 25? Write the equation of the tangent line to the graph of y equals natural log x squared plus e at x equals 0. Do that real fast and I'll catch up with you. What do you need to write the equation of a line? Okay, we need a point, and we're going to need a slope. If x is equal to 0, let me move this out. If x is equal to 0, where do I find the y value? Substitute right in there. So we have natural log of 0 squared plus e, which is natural log of e, and everybody knows that's equal to 1. All right, let's find the derivative, which is the slope of the curve, slope of tangent line to the curve. The derivative of log x squared plus e is 1 over x squared plus e times 2x. Okay? Don't forget, chain rule, 1 over the function times the derivative of the function. All right, when x is equal to 0, I'm going to get a 0 over e, which is equal to 0. So the slope is 0. What kind of line has the slope 0? Horizontal line, right? Horizontal line. So if you weren't thinking, you still could write y minus the y coordinate equals the slope times x minus the x coordinate if you weren't thinking, but you'll see that that is y minus 1 equals 0 or y equal 1. So a horizontal line y equal to 1 is the tangent line to that curve at x equals 0. Okay? Everybody good? All right, on page 269, your properties of logarithms. Properties of logarithms. Can somebody tell me why you think the natural log of 1 over x is simply minus natural log x? How would you show that that's the case? Okay, all right, that wasn't the direction my brain was going, but that's absolutely perfect. You did natural log of x to the -1, and then you're using your property that that is equal to minus natural log x. Okay, all right, anybody else got another way you could figure it out? What can you do when you have a quotient? Subtract. So you'd have natural log of 1 minus natural log of x, and what's the natural log of 1 equal to? 0. So you had two ways to do it. Great. So yours was to take this -1 and put in front, and there you go. All right, so can't miss it. I hadn't even thought about that. Okay, in this section you were doing some playing around with differentiating functions that looked awful. I always give you one of these. And what you wanted to do was write it in simplest, oops, we didn't do that one. We just did problems like number 4. Sorry. Number 5, we didn't do log differentiation, like example 5. Be sure you omit example 5. Here was one where you had a problem that looked awful. Natural log of x times x plus 1 times x plus 2. Your test question, unless I change from what I've done for the last 20 years, plus 20 plus years, is I always say write in simplest terms using your properties of logarithms. You can look at old tests and it's always there. And then I either say differentiate or just write in simplest terms. Okay, so you remember that when you had a product, you simply added. Now, you had not taken the derivative. I keep saying that because people in the past, if you were supposed to differentiate, once they used the properties of logarithms, sometimes they quit because they're in a hurry to go to the next problem. All you've done is just changed it to an equivalent value. Now you differentiate. Now you differentiate. Okay? We had a good time with those problems, best I remember. Okay, the homework in section 4.6, it starts out just giving you a little bit of quick review with logarithms using the properties to write as a single expression. How would you handle number 7? How would you simplify that?
Let's ease a problem.
Okay, so before you simplify it, you need to write that as e to the natural log of x squared. And now what is that equal to? X squared. We saw that yesterday when we were doing some integrating. You had something like 2 log something or 3 log something. We had to simplify it before we could get our final answer. Okay, let's see. The problems that we had a great time with were on page 273, problems 33 through 42, where we wanted you to write in simplest terms. And remember, there was some with like a e to the 5x, and you simplified that down before you ever took a derivative. So write it in simplest terms using logarithms, and then differentiate term by term. Okay, everybody good there? All right, flipping over to chapter 5. The new biggie in chapter 5 from pre-calculus was that differential equation, such as in problem number 1. P of t is the population of a certain city t years after 1990, and it satisfies the differential equation, not difference, as we did in the beginning of the semester, differential equation. And P prime of t, remember that's change in population with respect to time, and our time is in terms of years, is 0.02 P of t, P sub 0 equals 3. Just looking at that, everybody, tell me what the formula for P of t is. 3 e to the 0.02 t. Okay. And which is the growth constant here? 0.02. What am I not going to tell you on the test? I'm not going to tell you use the differential equation. I would say something like determine how fast. How fast. That tells you a rate of change. How fast is it growing? How fast? When it reaches 4 million people, what would your units be? What would your units for P prime T be? People per year. People per year. Right? P of t is the population in a certain city, so we assume that's people. Aliens, okay, per year. All right. We saw that was a growth kind of problem. We had a couple things with, like, for example, problem number 3 on the next page. Since the, is that a positive? That's positive. We had negative. Where's negative? Bottom page 285. Sorry. Number 14. This is the population, and you have a negative growth constant, so we call that a decay constant when it's negative. That just means it's going down. What's your formula for P of t here? 12 e to
negative 0.0432.
And this happens to be, what would be the units for the derivative here? Grams per year. So that would tell you how it's changing, grams per year. All right, that was pretty easy stuff, wasn't it? It wasn't too bad. All right, and then we did money, compound interest, compounded continuously. And the problem we did in class was number 2. It's just telling you if your money is earning 4.5% compounded continuously. And that's an annual rate, and it's pretty equivalent to compounded daily. It's good for just approximating things. You can make a lot of financial decisions quickly using shampoo, P-E to the R-T. Okay, those weren't too bad, were they? All right, let's go to 6.1. 6.1. Let's make sure I covered everything in 6.1. Okay, I'm on page 318 in 6.1. Okay, this was where it was just a little bit of confusion the way they used little f's and big F's. They used little f to mean a derivative and big F to mean the function. F of x, little f of x was their derivative. When I was working with you, I basically said the integrand was the derivative, find the function, and that seemed less confusing. But in problem number 2, it's just asking you to find the antiderivative, and what we would have done would have been integrated x squared dx, and that seems easy to you now. What would that be? X cubed over 3. X cubed over 3. Okay? And there it is right there at the top of the next page. All right? It looked hard in the beginning. What would be the antiderivative without looking at the right answer of e to the minus 2x? It would be. Now, I taught you this as a u substitution. The book wanted to teach it to you as to memorize another formula, and I held off because I was doing 9.1. But yes, when you integrate this, this is your u. Its derivative is minus 2 dx. So that's how you're going to come up with your minus 1/2, which is right here, e to the minus 2x plus c. Okay, flipping the page. They told you that this is page 320. That's the integral sign. We got that. This thing is called an indefinite integral. What would make this look like a definite integral? Okay, it had some limits on the integral sign. And it stands for antidifferentiation of that function. So this part is the derivative, and this is the function. And we found we could check those. All right, it was nice in this chapter. At the top of page 321, you had your first little rule, x to the r dx, r not equal to -1. Remind me again, if r is -1, what is that? 1 over the x, which leads to natural log. Okay, this is where they wanted you to memorize e to the kx is 1 over k e to the kx plus c, and I held off because you were going to learn to do substitution anyway. All right, down at the bottom, the integral 1 over x dx, natural log absolute value of x plus c. Okay, don't forget those absolute values. And on WebAssign, some of you missed it because you didn't put ABS for absolute value. All right, top of page 322. This says that you can integrate term by term. Integrate term by term. Integrate term by term. The second one says when you have a number, a constant, times a function, you can just say it's the constant times the integral of the function. We saw that when we had things like the integral of 1/3 x to the 4th dx. This is a constant times the function, so it's 1/3 times x to the 5th over 5 plus c. We did not learn if you had a function times a function in here. That's called integration by parts. That's next semester. And that's the reverse of the product rule for the derivative. So that's next semester. Okay? All right, bottom of page 322. here you were supposed to find a function when you were given the derivative and a point on the curve. We know that when we integrate and we find the function, it has a plus c. And that represents a whole lot of functions. But we want the one in particular that passes through that point. So once we integrate that, which is done right here for us, then this point, 1/4 allows us to solve for c. And there we have it right there done for us. Okay? Please wear out your book. Didn't you pay a lot of money for this? Gosh. $80? Might have paid more than that, yeah. They're expensive. All right. Would you look at 6.1 and tell me if there's anything on these pages that you think we need to look at? Which one?
Anyone where we can
Look on page 324, 325. Which one?
13.
Which one?
13.
16, 17, and what else?
13.
13. 13, 16, 17. All right, let's try those. All right, 13, 16, 17. All right, this is page 324, number 13. We have the integral of 2 over x plus x over 2 dx. And that is, we have two terms, so we're going to integrate term by term. All right, let me just rewrite it that makes me happy. 2 times 1 over x plus 1/2 times x dx. I think it's easier to see if you rewrite it like that, don't you? All right. So we're going to integrate term by term. If you feel better, you can rewrite the whole thing as two integrals. That's what your theorem just said. You can integrate term by term. Terms are separated by pluses or minuses. All right, so what do you get when you, this is a constant times 1 over x. So what do you get when you integrate 1 over x, everybody? So it's going to be 2 times natural log what? Absolute value of x. And now we have 1/2. And if you integrate x to the first, you get x squared over 2, and then we go plus c. So it probably looks best if you wrote it 2 natural log absolute value of x plus x squared over 4 plus c. Okay, who asked me this? So, okay, tell me what was really concerning you on that problem. Look weird. A lot of times when you have fractions, they do, especially if you got a constant, but if you write it as a product, I just think it's so much easier to see. Is that okay? Are you good now? Okay, so that was 13, and the next person said they needed 14? 16 or 17, okay? We'll look at both of them because integration is extremely important. 16, we have 2 over the square root of x plus 2 square roots of x dx. All right, did you want to break it down into two integrals? You do? Okay. All right, so how are you going to handle that square root of x in the denominator? So it's 2 times x to the negative 1/2 dx plus the integral of 2 times x to the 1/2 dx. Okay? All right, so we have 2 times, and all right, so we'll add 1. A lot of times if you'll just put a little plus 1 there, you make less mistakes. So negative 1/2 plus 1 is positive 1/2. And what happens when you divide by half? Invert and multiply. Okay, so divide by half is the same thing as invert and multiplying by 2 over 1. Okay, and let's see over here we have 2 times. All right, now we're going to add 1 to that 1/2. So you'll get x to the 3/2. And when you divide by 3/2, it's multiply by 2/3. Then we got a plus c. So it looks like we'll have 4. Do you want to use the square root of x, or you can still leave it as x to the 1/2? It doesn't matter to me. 4 square roots of x plus 4/3 square root of x cubed if you want. Okay, or you could just say x square roots of x if you want to simplify that. All right, was that good? What was bothering you?
I think I was leaving the C off.
Leaving the c off? Don't forget to leave. Well, you really could have left it as x to the 3/2. You didn't have to come down to this. All right, let's look at number 17. Just make sure we got it set up right. Okay, 17. The integral of x minus 2x squared plus 1/3x dx. The third term here is what gets missed a lot on my test. How are you going to rewrite this? I know you can integrate x. What is it? X squared over 2. What's the next one? 2x cubed over 3. Now, how are you going to rethink this integral of 1/3x dx? Yes, very good. 1/3 times 1/x dx. All right. So when you integrate 1/3 times 1/x dx, what are you going to get? Perfect. Okay. And again, that part gets missed a lot on tests, so be careful there.
Just remembering the rules.
Yes, the rules will always get you. All right, is there anything else in 6.1 that is bothering you when you're looking at it? We're good? Okay, 6.2, good old Riemann sums. Bottom of page 327. We see those words, area under the curve. First of all, this one is restricting it to be, well, it has to be continuous. And in this little part, it's going to restrict it to a non-negative function, meaning that the entire graph is up above the x-axis or touches the x-axis. All right, because that's the way they're going to introduce to you Riemann sums. All right, so they will call this area to be the area under the graph of the function from a to b. All right, they restricted it to be non-negative, so you didn't go below the x-axis. So they had a whole lot of pictures here to show you that. All right. Where is all this stuff? Riemann sums. Basically, you are, where's a good example? On page 334 at the bottom. Whatever this picture happens to be here. This looks like time and flow rate in liters per second. It went with the problem. Okay, to approximate the area of the curve using Riemann sums, remember we get intervals of equal width, and so wherever you start, you go like 2 minus 0, and if you wanted to divide it into 10, you would divide by 10. N is 10. All right, once you know your interval, you're either doing left endpoint, right endpoint, or midpoint. If you're doing left, put your hand on that interval, take your left hand, go up and get the y value, and bring it across to your other hand. That will tell you how high. You're using your left hand in your interval to tell you how high the thing is. That's your y value. If you're using right endpoints of your interval, use your right hand and go up and find the y and come to your left. Right, only your right hand gets to move. Okay? If you're doing a midpoint of an interval, what do? Go to the middle of the interval, go straight up and spread it out. Okay, like a goalpost for a touchdown, football. Okay? Make a T. Okay? Go up and make a T. All right? And a lot of times, I think even if you look at my old test, sometimes because I'm not letting you maybe use a calculator, you're just going to put the numbers in. For example, let me just tell you. Suppose you had the function y equals, log of x squared plus 3, for example. And we were going to, let's do this from top just because I want you to know what the instructions mean if it says just put in all the right numbers. All right, so y equals natural log x squared plus 3, and we're going to go from, say, x equal 1 to x equal to 5, n equal to 4. All right, so the instructions on the test say use Riemann sums to approximate area, and we're going to use, what do you want to do, midpoint, right point, left point, your choice. Midpoint, midpoint. All right, now we may not know right off what this graph looks like, but when x is equal to 1, clearly that's a positive value. 1 plus 3, natural log of 4. Okay, that's clearly a positive value. And when you put a 5 in there, that's clearly bigger than when it was at 1. So just sort of make yourself a little curve. I don't know exactly what it looks like, and we don't really care at this moment. All right, what is delta x here? 5 minus 1 over 4. So that's going to be 4 over 4 or 1. All right, so come down here and mark it into 4 equal intervals. So the next one's going to be at 2, 3, 4. Okay? All right, now we're going to do midpoint. So we've got to find our midpoint. What's halfway between 1 and 2? Okay, 1.5 is fine. 3 over 2. Let's do 1.5 because we never did it that way. All right, and then this one would be 2.5, and this one would be 3.5, and this one would be 4.5. Okay. All right, so our area then is going to be approximately equal to, and these are all heights times widths. Okay, and all of our widths in this case are 1. All right, they're not always 1, but they are here. All right, so here's my first little interval between 1 and 2. We go up through the middle and make a goalpost, touchdown. That is what a goalpost looks like, isn't it? I haven't been to a football game in so long. Oh, is that upside down? Okay, this is a swing set. Swing. Okay, but we go up to the middle and we make a T. All right, go up to the middle. All right, this is the y value when x is 1.5. So y equals the natural log 1.5, and we would square it and add 3, right? Isn't that the y value? So if on your test it said just put in numbers but don't simplify, you would say natural log 1.5 squared plus 3 times 1. That's the first one. Okay? And you tell me what the second height is going to be. Yes. Natural log of 2.5 squared plus 3 times 1. Okay? And this is all you would do on your test if it said just put in the numbers only, because you don't have a calculator. Because, you know, I figure if you got a calculator, it's just finishing this up. All right. And the next one is 4.5 squared plus 3 times 1. Okay? All right. So a lot of times that's the way I ask you a Riemann sum. Just get it there with all the right numbers and then quit. All right. We're good with Riemann sums? All right. Then in 6.3, we go with the definite integral. Let's see. Fundamental theorem of calculus, the bottom of page 388, 333, 338, sorry, 338. We're on page 338. 338. Fundamental theorem of calculus, if we have a function that's continuous on a closed interval, then let f, big old F, be the antiderivative of f of x. It basically says integrate and evaluate from top number minus bottom number. Okay, fundamental theorem of calculus. You have to have an interval that is continuous. You got to be continuous in order to be able to integrate. Okay? Basically, let's see here. What else is in here? A whole bunch of integration. Page 345. 345. Do you see anything on here you think we need to look at? Any problems? Number 22. I was just looking at number 22. That's probably a good one to do. Okay, number 22, right here. 22, integrate from 1 to 2, x over 2 plus 2 over x plus 1 over 2x squared dx. All right, let's do that real fast. Go for it. Number 22. Help me with this third term, 1 over 2x squared. How are you going to rewrite that?
1 over x raised to minus 2.
Okay, so it's 1/2 times 1 over x squared. And how are you going to deal with 1 over x squared? X to the negative 2. Very good. All right, let's have true confessions. Anybody miss this part right here? Did anybody write that as 2x to the negative 2? 2x to the negative 2? Good, I'm glad you didn't. I think we finally got that straight, haven't we? All right, that was the reason I was wanting to look at number 22, was just for this part. So let's just get the integration real fast. If you integrate 1/2 x, you get what? X squared over 2 times 2, which is 4. X squared over 2. And what's the next one? 2 natural log absolute value of x. And what's the next one? Minus 1 over 2x. I'm skipping some steps, but I think you can see what's happening. You're going to add 1 to this. So that makes that an x to the negative 1. Divide by negative 1 made that negative. Oops, we didn't need a plus c, because we're going to evaluate from x equal 1 to x equal to 2. Okay? All right, I'm not going to continue there because I'm watching the time, but what's the next thing you do, everybody? Which number goes in first? 2, and then don't forget to use big parentheses, minus whatever it is with the 1. Put in the 2's first, put in the 1. Be careful here. All right, is that good? All right, 6.4, extremely important. Extremely important. Areas bounded by curves. Page 348. Areas between two curves. The area of the region between the two curves from x equal a to b is, you have to know which one's the biggest. Top curve minus bottom curve, dx. Okay, you got to know what the graphs look like. Page 349, they're giving you a graph in figure 3, figure 3, and notice that the top and the bottom curves are changing. Top and bottom curves are changing. If you look lower on the same page, right down here, it shows you how we go from 0 to 1. That was the top curve in red, minus the bottom curve dx. See, y'all thought I just made this up if you hadn't been reading your book, but it's all right here. And then you pick up from 1 to 3, and your top and bottom curves are changing. Okay? It's all right here. Practice, practice, practice the examples in your book. All right. Page 351, example 4. Here's the graph of a good old parabola. By the way, if you didn't know right away how to graph your parabola, how do you use your derivative to find your vertex real fast?
Derivative.
If you take your derivative and set it equal to 0, solve for x, that's going to give you the x coordinate of the vertex, right? Because that's where you have your horizontal tangent. And then you know the y-intercept is 3, so you can pretty much get a quick little graph there. And then you know how to graph lines. This one, if you weren't careful, when you graph, it'd be hard to tell which curve is on top and which is bottom. So if your curves start to get on top of each other, you need to spread out your units, check some numbers in between. And it's usually between -1 and 1 that it's so hard to tell which is on top and which is on bottom, unless you do spread out those units. Okay? Alrighty. Anything on page 354? I think we did those pretty good yesterday. Remember, you have to set the two curves equal to each other to find their points of intersection, the x coordinates. Got to be able to see it. Okay? All right, 6.5 starts next after next class. We jump to 9.1. 9.1. Okay, you had 3. Where are they? Where's my U substitution rules? Did they not write them out for me? They didn't make it real clear for the U substitution, did they? You don't have a little box there for us? Well, gracious, we need to complain. They should have put it in a box for us. Well, I'm going to write it here.
There's one box, but these are words.
Yeah, those were, okay, they were using words. Our forms are u to the r du, r not equal to -1. Just like x to the r. 1 over u du, that's the case where r is -1, by the way, and e to the u du. Those are the only 3 that you're responsible for. If you pick the wrong u, it's not going to match up. It's not going to match up, so you go back and try something else. Okay, everything's got to match up just right. I feel like we did a lot of these already, don't you? We're okay. And then 9.3. 9.3, remember I went through and told you those you couldn't do yet because you don't do integration by parts yet, which is 9.2, some other integration techniques. All right, you know, looking at number 11, I know we've already done this, but you know to look to see if this is a 1 over u du, because that entire denominator here is to what power? The first power. That's the key to know that one versus number 8. Number 8, that's raised to the 4th power. So that one would be a u to the r. And this one, because the entire denominator is to the first, it's going to be a 1 over u. Okay? All right. Everybody good? Can you do it? All right, great. Everybody make 100 and I'll be happy and you will too. Make it a great day.